Swayam Prabha. Digital India. Educated India.
So, we are looking at how we can possibly measure viscosity using whatever we have learned so far. And the idea is, if the flow is one dimensional, I mean for the Couette flow problem, I told you that you measure the velocity, the force at one plate which you are moving at a constant velocity. Basically you find, because the velocity is constant, the force you are applying is balanced by the viscous stresses, and the viscous stresses depend upon the viscosity, and that is the concept you use to measure the viscosity. Okay. But it is not possible for you to have infinite plates in an experiment and do this. So, how can you translate the basic idea to an experimental setup? That is the question. Okay. And we are going to see one way by which it is done today, and that is what is called the Taylor-Couette flow. So, this is a modification of the classical Couette flow problem in rectangular Cartesian coordinates, and this is done in cylindrical coordinates. The idea is that you have two concentric cylinders, okay, and this is, let us say, R equals A and or R in, and this is the inner radius, and this is R out, outer radius. So, I have two cylinders exactly having the same axis, and the liquid is here. This has the liquid. So, the walls which are surrounding the liquid are basically circular in nature, okay. And to take the idea from what you saw in the last class, what you do is you keep the outer wall stationary, okay, and you rotate this inner cylinder at a particular speed, omega, okay. Omega will be in terms of radians per second. So, the inner cylinder is rotated at a particular angular frequency. Now, you have exactly the same situation, at least qualitatively, one wall which is moving with an angular velocity, another wall which is stationary, and the liquid is basically confined between these two, the liquid whose viscosity you want to measure, okay. And so, this is like a Couette flow problem, only thing is it is in cylindrical geometry, and this is called the Taylor-Couette problem, okay. This is again a classical problem. Now, the idea is, if this omega is low, okay, then the flow is one dimensional, and we will see what it is. As we increase omega, the RPM or the RPM, okay, then the we develop, or the system develops vortices, okay. Now, I am just telling you this because this is again, like I said, a classical problem. What do I mean by vortices? So, if I look from the top, okay, what is this 1D flow? One dimensional flow means, if I look at the top view, I have a cylinder here, I have a circle here, I have a circle here, okay. This is the inner cylinder which is rotating at omega, okay. The liquid is going to have only the tangential component of velocity, the theta component of velocity is going to be present. This is the 1D flow that we are talking about, okay. This inner cylinder is going to drag the fluid next to it, that will drag the fluid next to it, and so you get a velocity field, and the velocity component which I am focusing on is only the theta component of velocity. That is the only component which is going to be present. If omega is high, and this is if omega is high, what's going to happen is you have vortices of this kind. If you look at the cross section, the fluid is going to show vortices. Okay, these are called Taylor vortices. Now, why do these vortices appear? Because we are having a cylindrical geometry. You have a centrifugal force acting on it, V theta squared by R. Okay, this centrifugal force is going to push the liquid out, and because there is a wall, it will come back because of continuity, and you see vortices. So, basically the point I am trying to make here is, if you did this experiment at a very high omega, you will lose the one dimensionality of the flow, you will get a more complicated profile. Okay. So, whenever you talk in terms of measuring viscosities, people look at low omega, low speeds, low viscosity. So, because you want the flow to be one dimensional, so that you can characterize it and you can calculate what the viscosity is. Okay, that is something you have to remember. You can't just say I am going to increase the RPM, because then the assumptions of one dimensionality on which the principle of the viscometer is based may break down. Okay. So, you need to do what you think about what you are doing. Okay. So, point is, these vortices, if omega is high, we have vortices arising because of the centrifugal forces. Okay, and flow is not one dimensional anymore. Flow is not one dimensional. Okay, that is something which you need to know. Now, since the axis is the same for both, okay, we will have a situation where as you go in the theta direction, there will be no change in the flow. Okay. So, because the cylinders are concentric, and this the axis is the same, there is no change in the velocity field with theta. Okay. So, if I look at, again I am going to redraw that those two circles. What do I mean by that? This is theta equal to 0, this is theta equal to pi by 2, okay, because theta is my angle, polar angle. I am saying the velocity here is the same as the velocity here. Okay, if you wait for a sufficiently long time. So, basically what this means is, theta symmetry means d by d theta is 0. That is the meaning of theta symmetry or axis symmetry. It is symmetric about the axis, it is symmetric about theta. Okay. Now, can you think of a situation where, okay, what does this mean? Another way to look at it is, supposing d by d theta is not 0, let us say it is positive at some point. Okay, what happens? There is no, it has to be, because this point is being chosen arbitrarily, it should be positive everywhere. Okay, one way to argue is that if it is positive here, you keep moving in the theta direction, the velocity keeps on increasing, because the derivative with respect to theta is positive, the velocity will keep increasing, and then you come back to the same point, you will get a different velocity. Okay, and that clearly is a contradiction. Okay, that is another way to argue. So, I mean, if say d by d theta of v theta is positive, then when we come a full circle, we will have a different value of V theta, right. As you go around theta, V theta keeps on increasing, will come back to the same point. So at say one point we had two velocities, so that can't happen, and therefore the only way we have the same velocity is dV by d theta is 0. Okay. Is there an example of when theta symmetry will not be there? If the cylinders are eccentric, means they are not concentric, they do not have the same axis. Okay. So what happens? I have this big cylinder here and I have a small cylinder not having the same axis. This has a separate axis, this has a separate axis, and now my inner cylinder is moving. Okay. The gap here is much smaller than the gap here. So the velocity here has to be much higher because the same liquid has to flow because of continuity. Okay. The velocity at 0, so this is v theta at theta equal to 0, and this is theta equal to pi. Okay. There is v theta here. So my point is v theta at theta equal to 0 must be much more than the v theta theta equal to pi, because the cross section available for the flow is much higher, much lower here. So v theta at theta equal to 0 must be greater than v theta at theta equal to pi. Is this correct? Smaller area, more velocity. So my point is, in the upper half velocity will increase, so the velocity will decrease. In the lower half velocity will increase. Okay. So v theta dv theta by d theta is greater than 0 in the interval from 0 to pi. Did I write it correctly? No. Velocity decreases in the upper half. Okay. So the derivative is negative. As I go around theta, velocity has to decrease, but in the lower half, which is from pi to 2 pi, the velocity has to increase because it is eccentrically placed. So I mean, I just wanted to explain to you that you can have situations where theta symmetry is not there, but in typical problems that we have, because the axes will coincide, we have theta symmetry. Okay. So that is basically just to give an idea. So rather than just do it mathematically, you have to understand physically that, see, as if the cylinder is rotating, it does not matter which one you choose as theta equal to 0. There is a it's same, it does not matter whether you choose this axis as theta equal to 0 or some other axis as theta equal to 0. So you should have theta symmetry. Okay. So now, having given this much background, let us see how we can proceed with our calculation and see basically some differences between the rectangular and the cylindrical geometries. Now we solve the same using the same approach, continuity, see what we can infer and then proceed. So the equation of continuity is, what is it, 1 by r d by dr of rvr plus 1 by r dv theta by d theta plus dvz by dz equals 0. So this is the equation of continuity, and because of theta symmetry, v theta is not 0, but v theta is not changing with theta. Okay, we are, as long as your cylinders are concentric. So this becomes 0 because of symmetry. Okay, and if the cylinders are very long, okay, this length is very long, if you focus your attention somewhere in the middle, you can say that things are not going to change with respect to z. Why am I focusing in the middle? Because closer to this wall will have some effect. Okay, there is a wall here which will have an effect. There may be a wall here which may have an effect. So I don't want to consider the effects of the wall, because in this portion and in this portion there will be a z dependency. Okay, so if we focus on the middle, then we can say d by dz is 0, and I guess vz is also 0. So basically I am trying to say that my flow is one dimensional, only v theta exists. Okay, is this clear? So near the bottom wall and the top wall, these wall effects may be dominant, so you may have other components of velocity showing up. So you need to, this is like a fully developed flow assumption we make, sufficiently far away from the inlet wall. Okay, so this is similar to that, and therefore we are saying we are focusing in the middle region. Okay. Now, so what does this mean? This means the equation of continuity simplifies to this equal to 0. Okay, and you can solve this and you can say r Vr equal to a constant, Vr equals C1 divided by r. So the radial component of velocity we are saying is 0. I mean, why are we saying it is 0? Because at r equals, what did I have? R in, the inner radius, Vr is 0. At r equals r out, Vr is 0. That is, the wall is solid, the liquid cannot penetrate it. Okay. Therefore, if Vr is at r equal to r in, r out, Vr is 0, this implies C1 equal to 0, okay, and therefore Vr is 0. So you can see that something very similar to what we did in the Cartesian coordinates is what we are getting here. Okay, we have one of the velocity components is 0, so there is no radial flow, and you only have the theta component of velocity. Now we will go to the equation of momentum, and then we will see what information we get. And because there are these additional terms which come, I decided to have these written on the board because I don't want to make a mistake, because all these additional terms is something which I don't remember. Okay. Now I just want to point out that these terms on the left hand side is what we have done in the class when we did v dot del v. Okay, we got these inertial terms. What I asked you to do is get these terms, del dot del v. Okay, these terms are coming from del dot del v, which is your homework, and this is what I did. Okay, this is del dot del v plus del v transpose, sorry. Those are these terms. Okay. Now, so when you actually do the evaluation, you saw how you got v theta squared by r, you saw how you got Vr v theta by r. Okay. When you do this evaluation, you will get all these extra fellows hanging around somewhere. All this r equation, you have a theta. Again, you have for the theta direction, you will have some Vr term. So, and all these are coming only because of this unit vector changing with theta. Okay. Anyway, but I think idea is you should know how to derive them, that is all. Okay. I am not expecting that you should remember all of this by heart. Okay. Now, let us see what information we get from the first equation. So, dVr by dt is 0 because we are saying it is steady state. Anyway, Vr is 0. We already showed that Vr is 0, right? So, this goes to 0 because Vr is 0. This goes to 0 because Vr is 0 and theta symmetry. This does not go to 0, v theta squared by r, because v theta is there. okay. This goes to 0 because Vr is 0, okay. In the radial direction, if the cylinder is vertical, in the radial direction there is no gravity, okay. This goes to 0. dP by dr, I am not putting it equal to 0, and because Vr is 0, all of these go off, and because of theta symmetry that goes off. All I am saying is you should cancel things with the right reason, okay. I am not cancelling this because V theta is 0, I am cancelling this because of theta symmetry. I am cancelling these, I am knocking these off because of Vr being 0, okay. So, in the r direction, what I am left with is minus rho V theta squared by r equals minus dP by dr, or I can make both of this plus. So, what this means is there is a pressure gradient which is developed in the radial direction, okay. In the radial direction you have a pressure gradient, dP by dr is not 0 because V theta exists, okay. So, basically if you have a particle, I think I can get rid of all of this. So, if I look at the circle, this particle is moving. So, what is preventing the particle from flying off in a tangential direction? What is keeping the particle constrained to move along a circle? Basically, at every point the particle is moving along a circle, right? This is the path taken by all the fluid elements, okay. So, what is preventing it from going along circle? The pressure here is higher than the pressure here. That is what is keeping the particle to move along a circle. That is the force. So, the particles are basically experiencing a force directed towards the center because the pressure outside is much higher than the pressure inside. dP by dr is positive, okay. So, fluid particles experience a force towards the center. This is your centrifugal force which keeps the particles along a circular path. The other important point which I want to make here is that these forces, the centrifugal forces, these are called, for example, pseudo forces or fictitious forces. They are pseudo forces because they are not occurring because of any gravity. There is no physical reason. If you remember, the V theta squared by r, they came because of this mathematical thing that the unit vector changes in the theta direction. That is the one which gave you this contribution of V theta squared by r, okay. I mean, it is not that like gravity is a physical force, electrostatic thing is a physical force, magnetic force is a physical force. So, V theta squared by r, people say it is a pseudo force because of this business of why it is mathematically it has arisen because of the fact that dEr by d theta is not 0, okay. So, that is the reason this is called a pseudo force. So, that is and the other thing I want to talk about here is what is the relationship between dP by dr. So, as you go further and further away, if your r is very large, this dP by dr will decrease, okay. So, basically r is the radius of curvature, the circle radius. At a particular r, what is the radius you know, that tells you what is the pressure gradient across that. But supposing it is a very large radius you are looking at, very large radius over which the particle is moving. Because r is large, you have dp by dr going to 0. So, in your rectangular Cartesian coordinates, the interface was flat, okay. There r is like infinity. So, like you are on the surface of the earth, earth is spherical, but still you are thinking it's flat because r is very large, okay. So, point is, in the rectangular Cartesian coordinates where my interface was flat, dp by dr or dp by dy, whatever the coordinate is, was 0 because the interface was straight, there was no curvature. dp by dr is coming only because of the curvature, okay, and that is what keeps the particles on the moving in a circular path, okay. So, I think you need to think about these things. Now, this is the information which I have. So, although I am not applying any pressure in the radial direction, the centrifugal forces are generating my pressure gradient, okay. Now, the theta momentum equation is going to give me at steady state, this is 0. Remember, theta, v theta is not 0, there is a angular velocity, okay. This is 0 because Vr equal to 0, okay. This is 0 because of theta symmetry, derivative with respect to theta is 0, okay. Now, this is 0 because Vr is 0. This is 0 because, I mean, we are not focusing on the center, therefore, d by dz is 0. Theta direction, there is no gravity, so that goes off. I am not imposing any pressure gradient. Like in the Couette flow problem of Cartesian coordinates, the wall was the one which was giving the flow. So, again here I am not imposing a pressure gradient, and so therefore, I am saying this is 0. Again same funda, you can't, or you will have to have pressure if you go in the theta direction. If dp by d theta is positive, pressure will keep on increasing, and at the same point you will have two different values of pressure. So, the only way you can have avoid this kind of contradiction is if dp by d theta is 0, okay. If dp by d theta is not 0, let us say it is positive, or it has to be positive for some distance, negative for some distance. So, physically how can that happen, right? So, you can therefore argue any which way you want and figure out that dp by d theta is 0, okay. What am I left with? Again, this is 0 because of symmetry, this is 0 because of symmetry, this is 0 because d by dz is 0, okay. What I am left with is only this term here. So, the v theta is going to be governed by d by dr of 1 by r d by dr of r vr equal to 0, r v theta, and v theta does not depend upon theta, it does not depend upon z. So, these are not partial derivatives, these are actually total derivatives, okay, same argument as before. And so, what I am saying is this becomes d by dr of 1 by r d by dr of r v theta equal to 0, okay, because v theta is a function of r only. So, you can, so that means this is a constant, I mean you can integrate this without any problem, equal to a constant. I can take this r over there and I can write d by dr of r v r or r v theta equals C1R. Again you do something here. What do you do? Is that right? Integrate this again. So r v theta is equal to C1 r squared by 2 plus C2. Okay. So v theta is C1 r by 2 plus C2 divided by r. Okay. This is just straightforward integration, okay, which you all know how to do. Now, so idea is you will find these constants, and these are constants, they are not functions of r and z, because they are not functions of theta and z, because you are ODE, okay. And what are the boundary conditions you are going to use? V theta equal to 0 at r equals r out, v theta equals, if omega is the radians per second, okay, the speed, angular speed, so I will have to get it in terms of centimeters per second, I have to multiply it by r in, okay, at r equal to r in. So, omega r in at this. So, at r equal to r in, the inner circle which is rotating, inner cylinder which is rotating, the angular speed omega, you look at the units, if I am giving you in centimeters per second, you do not have to do anything, but if I am giving you in radians per second, you have to convert it by multiplying it by a. If I am giving it RPM, you have to convert it, okay. So, anyway at the end of the day, you want the angular velocity. So, basically I am not going to do this, you have to substitute these two boundary conditions and solve for v theta, solve for C1 and C2, okay. So, find v theta from the using the boundary conditions. Okay. So, now that you know what is v theta, then you can substitute it back here and find out how the pressure is changing in the radial direction, okay. You have the expression of v theta, you can get that, but our objective is to find the viscosity, okay, and the way you would find the viscosity is by looking at what is the shear stress. To find viscosity, find the shear stress on the inner cylinder, because the omega is constant, okay. So, how do you find what component of shear stress are we interested in? What is the radial outward normal for the inner wall? Outward normal will be the radial direction, okay. So, the first subscript I am interested in is r, because that is the direction of the outward normal, and I am interested in the tangential direction, which is the theta direction, because the flow is in the theta direction. So, I am interested in tau or theta, that is the shear stress, okay, which we have to find out, okay. And I am going to try and remember what I derived yesterday. What was it? Mu times r d by dr of v theta by r, okay. I think this is what I derived yesterday. I think there is a one more term minus Vr by r, is it? Can we just check? Okay. I think the first part is right, the second part I do not remember now. I think this is Vr by r. Anyway, it does not matter, this does not contribute because Vr is 0 for us, okay. And I am saying that this guy is mu times r dv theta by d by dr of v theta by r, okay. And I have to evaluate this at the inner cylinder surface. This has to be evaluated r equals Rn, okay. So, this expression for tau r theta, I am just remembering, can anybody confirm if this is right? Towards the beginning of yesterday's class, I had tau r theta. I knew I was going to use it today, yeah? This is dou v r by dou theta, is it? Dou v r by dou theta. Okay, so this is wrong. 1 upon r dou v r by, okay, sorry, yeah, I don't remember, okay, plus or minus? Plus, yeah, okay. It doesn't matter, it goes to 0 because Vr is 0, okay. Idea is I know V theta, which I already found out, I will substitute it here, I can calculate this. Now, because I am rotating this, what am I going to measure? I am going to measure the torque required for the rotation. So, experimentally, what my viscometer does is, it keeps rotating the inner cylinder. There is a specific torque which it applies to keep the omega constant, okay. So, what is going to be the torque? Is going to be whatever is the force will be tau r theta multiplied by the area, this is a shear stress, multiplied by the area is going to be the circumferential area, 2 pi r in multiplied by the length, that is the area over which the shear stress is acting, 2 pi r in multiplied by L, okay. This is the force, this is the force, and to get the torque you have to multiply it again by Rn, R cross F is the torque, okay. So, tau r theta tells you the shear stress acting on the inner cylinder, okay, pointing outward in the radial direction along the theta, multiplied by the area over which it is acting gives you the force, multiplied by the R to give you the torque, okay. So, basically what the viscometer will do is it will measure the torque, okay, and there is a viscosity string inside here, tau r theta you already know, and you know V theta for a particular RPM, you already calculated the flow, so you can calculate all of this and you can find what the viscosity is, okay. So, this is one design of a viscometer which is used. So far, whatever problems we have seen, we have assumed that things are at steady state, things are not dependent on time, okay. So, what I want to do is look at some problems now where things are actually going to change with time, okay, and we about 2 or 3 problems we will look at. So, systems where the flow changes with time, okay. So, supposing you have a cylinder R equals R naught and you impose, and there is a liquid in the middle at rest, okay. This is filled with liquid, and all of a sudden you apply a pressure gradient, okay. You apply a delta P, delta P. So, what are you going to get? Let us say delta B is sufficiently small, so you eventually get a laminar flow, the parabolic velocity profile. But the question you may be interested in is, how much time does it take for the system to attain this parabolic velocity profile? Do you have to wait for 1 minute? Do you have to wait for 1 hour? Do you have to wait for 1 day? What is it that is going to decide the time? So that if you are going to plan your experiment, okay, you can plan your experiment so that you can get steady state as quickly as possible. But if you are in no hurry, you say no big deal, I will come after 1 month, let the steady state come, that is a different story, okay. So you may be interested, supposing I am wanting to run an experiment in the lab, I want to get to a steady state as quickly as possible, right. I want to finish my experiment in 3 hours, I can't wait for 3 hours for steady state to achieve. So what is the time taken to attain steady state? Okay, this could be a question, okay. So what is the time taken to reach steady state? The steady state is, of course, is the parabolic profile, okay. This will help design my experiment or process. Another example where we may be interested in transient flow is the flow of the blood through the arteries, okay. You know that the heart is pumping periodically, you have this lub dub sound, okay. So the flow of the blood through the arteries, the pressure which is going to be felt by the blood is actually periodic. The heart is not giving you a constant flow rate, not a constant pressure drop, okay. So if you want to, this is another situation where you can have the flow of blood through the arteries and veins, okay, is subject to a periodic pressure drop. What I mean by that is delta P is some periodic function, maybe some constant A multiplied by 1 plus epsilon sin omega t, okay. The pressure is varying periodically in time. So clearly you can't get steady state because the blood will, if the pressure drop is high, it will flow more, if it is less, it will flow less. So there are situations where the velocity field will change with respect to time. What that means is, I cannot put d by dt equal to 0, okay. So far we have always looked at steady state problems, and there are other problems also which we will possibly look at where things are going to be time dependent, okay. So that will be the focus of the next few lectures. Then we will look at maybe importance of making things dimensionless, but I might do that even as we discuss these problems, because so far what we have done, we have not focused on dimensionless numbers, how to do scaling, okay. So to analyze the problem, I mean I have just told you how to derive equations, but after you derive the equations, an important part is how do you do the scaling, how do you choose scales to make the variables dimensionless, because that will help you determine which are the important effects to consider and which are the insignificant effects which you can neglect, okay. So we will see all that and then we will proceed. Thank you.